Okay, hi class. This lesson is going to be focusing on a bit of a review. We've looked at the solubility chart before, and we've seen how to predict the formation of a precipitate from the combination of two ionic compounds in solution. Um, when we use this table, we're really looking at a physical property of a compound, which would be its solubility. And if a particular combination produces a unsaturated solution, then no precipitate will form. We sort of describe that situation as high solubility. When the combination of two aqueous solutions produces a saturated solution, then we expect precipitate to form, and we classify that as low solubility. So under the low solubility, we can have any combination of anions and cations. It's very difficult to predict from the periodic table where high and low solubility occurs, but there's some trends you may have observed. For the most part, as long as you can interpret the table, what we're also going to do in this lesson is extend our understanding of precipitation reactions to the writing of ionic equations which focus just on the ions which are participating in the reaction. We call those net ionic equations. Let's just watch a couple video clips just to review the principles of solubility first.
When solutions of lead nitrate and potassium iodide are mixed, solid lead iodide precipitates from solution. The liquid remaining in the test tube is a saturated solution of lead iodide. Whenever a precipitation reaction occurs, the solution surrounding the precipitate is saturated with the product of the reaction.
All right, so that was just an illustration of the saturation point. When the saturation point is reached, a precipitate is formed. We saw the nitrate of lead, which would be soluble, as all nitrates are soluble. We saw the iodide of potassium mixed together. So those are the solutes that are dissolved in water to make a solution. And in this case, saturation occurred because the combination of iodide and lead 2+ has low solubility. So there we see that the precipitate forms, but the solution surrounding the precipitate still contains a maximum concentration of lead 2+ and iodide ions. So there is still the potential for more precipitate to form if the amount of solvent were to be reduced. That could accomplish that, or if the temperature were to be lower, that quite likely would also cause more precipitate to form. Now, having used the solubility chart before, we want to focus a little bit more in this lesson on the construction of these net ionic equations. So if we look at first sample problem, we'll illustrate this. When we're given a balanced reaction equation, we look at the states of matter and we identify all those which are aqueous. Those which are aqueous we understand to be ionic compounds where the ions are surrounded by water molecules. And in this case, we can show the dissociation or separation of those ionic crystals into individual ions. So anything that is an ion that's aqueous in its form can be written separately, and we'll do that on the left side and the right side. That would show a total ionic equation. So the total ionic equation represents all aqueous ionic compounds. When we look at the overall reaction, we see that some ions are not really participating in the reaction. They're what we call spectator ions. And a spectator ion here, appearing on the left side and the right side, does not affect the formation of the product. Therefore, we remove them in the final equation, which is called the net or overall ionic equation. And so this is a really simple process here, and it just helps us to isolate which reactants in particular are involved in the formation of this ionic precipitate. So in that case, barium sulfate would be the product from the combination of barium 2+ and sulfate. In this case, sample problem 2 has zinc metal and aqueous copper 2 sulfate. So this is a single displacement reaction. And here we're trying to write, again, the overall ionic equation, which first requires us to write the what you might call the non-ionic equation. And a non-ionic equation shows no ions, but it shows all the participating reactants in their full form. You'll see non-ionic referred to in the sample problem here, student worksheets rather, non-ionic, complete ionic, and net ionic. So the complete ionic would be what's being referred to before as the total ionic. The non-ionic could just be the overall reaction equation. Make sure it's balanced, of course, in all cases. So if we return to this sample problem here, zinc plus copper 2 sulfate forms copper and zinc sulfate. Now in this case, this is the formation of a solid element. It wouldn't really call that a precipitate exactly. There's a electrical chemical reaction which is taking place, which is changing the form of copper from ionic to neutral elemental. But we would also need to know in this reaction that zinc displaces copper. So that's just one thing to take note of, that in order to predict the formation of products in single displacement, we have to know the activity series. And in this case, zinc does displace copper. So having referred to an activity series chart, we would be able to, in this case, predict the formation of the product. Then we can write the total ionic equation, which shows all soluble or aqueous ionic compounds dissociated or broken up. Solid zinc is not ionic, so it remains as a solid form. Copper as a product is not ionic, so it remains in solid form. And then once we examine the spectator ions, they get removed and the net ionic equation is written. It'll look a little bit odd sometimes when you write a net ionic equation because it doesn't at first appear that anything has happened. You have, zinc plus copper going to copper plus zinc, but you really have to pay attention to the charge of the ions and the change in the form of the element. Okay?
When a solution containing iodide ions is added to one containing lead 2+ ions, a precipitate of lead iodide forms. This precipitation reaction occurs because lead iodide is an insoluble ionic compound. Hydrated ions release water molecules and form the ionically bonded solid.
Okay, that little clip there was just shown just to give a little bit of appreciation for what occurs when the precipitate comes out of solution. So prior to that, the ions are kind of chaperoned by water molecules. They've been broken up into small enough pieces that they're classified as dissolved ionic solid. And then once they come into contact with another ion which has low solubility in its presence, then of course the precipitate forms, and then we have that saturated solution surrounding it. So let's move on and look at the student worksheet here. And in this case, we're just going to be writing the non-ionic or overall reaction equation. Zinc combined with silver nitrate. Okay, this is an element in a compound, so we should be thinking single displacement. We're looking at zinc and silver, which is has very low activity or reactivity. So zinc is certainly higher by quite a bit. So this reaction will take place when we look at writing the net ionic equation. We just do this in stages. So the overall reaction shows all of your reactants in their appropriate forms. Make sure it's balanced. Zinc has a 2+ charge, so nitrate, there'll be 2 nitrate ions in the product. And in this case, for the total or complete ionic, we just divide all the aqueous into the dissociated ions. So we have 2 silver, 2 nitrate, 1 zinc 2+, and 2 nitrate. So remember, the coefficient in front of the ionic compound applies to all the ions in that compound. Then once we identify the non-reacting ions, which in this case is only one, which would be the nitrate, we remove it, and in the final or net ionic equation we just write all of the reactants or ions in the form previously, and that would be our overall reaction. All right, so in this reaction, this is a double displacement reaction, and both reactants are highly soluble. We can confirm that with the solubility chart. So we have nitrates and chlorides. So if we go back to the solubility chart, we find that most chlorides are soluble. All nitrates are soluble. In our reaction, of course, we're forming a chloride with lead 2+. Lead 2+ is the most common ion form of lead. And in that case, we would expect the precipitate to form with the combination of chloride and lead 2+. So we predict a saturated solution. You can almost think of the S in the product as representing saturated, although really it represents solid. But that can remind you that you've saturated the solution with ions. You have as many ions as possible before precipitate forms, so we get a solid. We balance it. 2 chlorides, 2 potassium are required to form our product, which is potassium nitrate. Now in this case, potassium nitrate is highly soluble, so we're just going to get an aqueous solution, which means we'll just have potassium and nitrate ions surrounded by water molecules. So whenever we write aqueous, we can think of aqua or water. Water is really attached to those ions, keeping them separate. So when we write our total ionic equation, we have a lot of ions to write there. We have lead, nitrate, potassium, chloride, and then we have potassium and nitrate on the right side. Potassium and nitrate are present on both sides, so they're spectating, they're not involved in the reaction, so they were removed, and in the net ionic equation we have our overall reaction for the formation of lead 2 chloride. Okay, just to sum up here, the steps involved in ionic equations, as you've seen, would be writing the balanced chemical equation first with all your chemical formulas and states of matter. Using solubility information, predict the state of matter for the products. High solubility ionic compounds as dissociated ions. That would be aqueous in form, and low solubility as soluble precipitates. We cancel identical amounts of entities appearing on both reactant and product sides, which are called spectator ions, once the total ionic equation has been written, and then we write the net ionic equation, reducing coefficients if necessary. That we haven't seen occurring. I think if the original equation is balanced, that's not going to happen. So the assigned work here is just a combination of some review. If you need a little bit more practice interpreting the solubility chart or predicting precipitate formation, you can try number 1 and 2, pages 333 to 334. If you're pretty comfortable with that, just look at finishing up the student worksheet here. I haven't done numbers 3 and 4, but you'll be able to complete those as your note. Make sure you have the definition of spectator ion. You can find it in your textbook on page 334 in the margin. Solutions here are on worksheet 7.3b, which will be posted on the website. And in the textbook, you can get additional practice by doing numbers 1 to 3 on pages 336 to 337.